Hello, everyone. Good morning. Welcome to the next in our webinar series. I think this is really important, this webinar series, as part of the Freshwater Quality Programme, helping to sort of share knowledge and understanding. So the programme as a whole, just as a reminder, is looking at how we can improve our understanding of the sources and behaviour of pollutants, and how those pollutants are changing and accumulating within the environment, and what are the impacts of those pollutants. And in the long term, really, what are the solutions to reduce pollutant loading to river systems? So how do we inform policy and practice to enhance the ecological status of UK rivers, and also then deliver the science that's needed to be globally leading in this regard? So how do we adapt and mitigate risks, both in terms of land management, but also in terms of future climate. So that's the kind of remit of the programme. Next slide, Finn. And just as a reminder again, that so we have a programme-wide activities, and the champion team involves myself and Pippa Chapman, and then also supported by Finn, who you just heard from, Finn Barlow-Duncan, and Anne-Marie Boyle, Kath Seal and Farhana Naz here in Water at Leeds as a host. But then we have these 5 really important and exciting research projects within the programme that we're supporting. And we'll hear updates from each of those projects in upcoming webinars. Next slide, please, Finn. So ultimately, what we're trying to do is use science evidence to improve UK freshwater quality. And there's obviously a number of ways you can keep in touch, and do please pass on to your networks the fact that we have this community engaging around webinars, but there'll be workshops and other activities around the programme. There's newsletters and so on. So please do forward the link to ask people to sign up to join. And you can watch past webinars if you're part of the networks, if you've signed up. They're not publicly available. They're available if you sign up to the link. So please do encourage your colleagues to do that. So we've had a couple of really great seminars so far. We've had a policy-orientated dual presentation, which is really important. Our last webinar we had, which was about thinking about how we engage community or citizen science data sets and protocols along the pyramid, and moving up towards, how you interact that sort of data with professional data sets and so on. And so that's been really useful, I think, in terms of generating dialogue around these amazing projects. So, as I said, in the webinar timetable, there's a set of meetings there you can see on screen coming up, which are more project updates. But if we move on to today's presentation, I'm absolutely delighted to welcome Magda Bieroza from the Swedish University of Agricultural Sciences. Magda's doing some really interesting research on water quality, particularly agricultural landscapes, but I think a number of other landscapes as well, and has some really exciting work on nutrient dynamics and carbon dynamics in these systems and more broadly, and also has been thinking a lot about the resolution of sampling, water quality sampling, and how different resolutions of sampling can provide insights into functioning of the land and water system. So Magda, we're really looking forward to today's presentation. We're so delighted that you could present to us. I'll hand over to you. Thank you.
Thank you, Joe. Thank you for having me. Let me just find my presentation. Okay, can you see it?
Yes, we can see it.
Right.
Thank you.
Right. So good morning, good afternoon. My name is Magdalena Bieroza, and at the moment I'm in Sweden. We have -20 degrees, sunny weather. However, some of you might maybe remember me from my time in Birmingham and Lancaster. High frequency water quality measurements, that's the topic I'm going to talk about today, and it's very close to my heart. And in my research, I use this technology both for basic research, so understanding how catchments operate in terms of different processes, but also for more applied angle. So how different land management and land use properties can affect water quality. So I guess I don't need to really explain or describe the high frequency technology to you. You are familiar with it by now. We had quite eventful 30 years, at least 30 years of those tools being available, and they vary from quite complex laboratory-based tools that we put in this kind of bank side analyzers, as on the left-hand side, to more simple probes that are operating on absorbers or fluorescence principles. So depending on what type of measurement we use, what analytical tool is behind those instruments, we can pretty much measure everything in terms of water quality, from quite simple parameters like pH, temperature, turbidity, to more advanced ones like nutrients, ions, isotopes, and FDOM, which is dissolved organic matter. The range of applications is quite broad. We have new tools coming up, like lab on the chip. So we're getting those instruments both smaller, more energy efficient, and cheaper. But also there is a scope for fusion with new technologies. So Joe has mentioned citizen science, and that's a perfect example where we can use high frequency measurements combined with citizen science approach, so we can establish both more robust but also larger sampling networks. And if you are not convinced what's the value of high frequency measurements, this picture, I hope, will provide the evidence. So in the dark blue, we have flow. So we have 6 months of hydrograph for Plinlimmon catchment in Wales, and you can see the value of high frequency measurements when you compare different sampling frequencies. If we move from monthly at the top to 7-hourly in the middle, as you can see, this is quite dynamic hydrograph, so we need quite detailed understanding of what happens in terms of stream chemistry. And even weekly sampling can conceal a lot of detail, a lot of processes that happen in this catchment. From more management perspective, we often are interested in calculating loads for different parameters. So here we have flow at the top graph in blue, and corresponding total phosphorus concentrations in milligrams per liter. And you have different frequencies of sampling, so from hourly as a solid black line to weekly. So you can see that, again, going into more finer temporal resolution, we can get a lot of more detail from our dataset. But what does it mean in terms of loads? So here we calculated phosphorus loads for over 80 days, and this is a cumulative load. You can see the spread compared in loads estimates between hourly, daily, and weekly measurements. Interestingly, we wanted to simulate what happens if we measure at any given day of a week, so Monday, Tuesday, Wednesday, Saturday, weekly sampling, and how does that affect load estimation. You can see that from Friday to Thursday you can get from severe overestimation to severe underestimation of your load. So this is another example showing why we need high frequency measurements and how they can be used. But of course, we are just at the edge of discovering all the potential for this technology. And it's not just a basic science, it's not just a catchment science, understanding hydrological biogeochemical processes, but also understanding freshwater ecology. We can measure stream metabolism with dissolved oxygen probes. So we can get more insights into functioning of entire stream networks. And of course, as many of the driving processes are non-stationary, we can also see the effect of global change, specifically climate change, on underlying processes and resulting water quality patterns. There is also great potential for providing evidence for management decisions, and I will show you some examples in my presentation later. So this is quite a broad topic, and you could spend probably the entire series of those webinars discussing just high frequency measurements. But today I would like to focus on one aspect, and that's concentration discharge relationship. As I said, the value of high frequency measurements is that we can match stream chemistry to stream flows. So here we have two graphs. The top one is discharge, so continuous hydrograph over several years. This is one of the subcatchments in the Eden catchment. And you can see it's quite flashy hydrograph with a lot of base flow component. And below that, we have total phosphorus concentrations corresponding to that hydrograph. So immediately you can see that we can, for pretty much every single storm event, see what happens with concentrations. So that allows us to discover or confirm some of the water quality patterns that are repeatable, so they possibly happen on a seasonal or daily basis, but also it provides a scope for discovering some new water quality patterns, so something that is maybe a little bit more random. And here, for example, the effect of climate change, effect of drought, it's a good example of those kind of stochastic events that we can use high frequency data to provide evidence of. So concentration discharge relationship, as the name suggests, shows the discharge versus concentrations, and it could be concentrations of anything measured, not necessarily at high frequency, but any water quality data that we have. And depending how much data we have, obviously with high frequency measurements, we can get a lot of data quite quickly. So we can get a little bit more robust or maybe improved understanding of those relationships. So I want to walk you through some terminology I'm going to use in my presentation. So first type of the relationship is the chemodynamic relationship, where we have a storm event, the flow increases, and correspondingly concentrations also increase. So that's a concentration effect. On the other hand of the spectrum, or the other side of the spectrum, we have dilution. So this is a situation when with the increasing flow discharge, we have dilution effect. And the last one that we see quite a lot thanks to high frequency measurements is the chemostatic one. And this one is very interesting because we have a dramatic change in flow, but we do not see as big response in water quality. So the concentrations pretty much stay conservative throughout the storm event. So we have those three different types of flashing patterns, and those have been shown to reflect dominance of different drivers. So the more chemostatic responses are driven by hydrology, whereas those more chemodynamic, they have a higher or more strong control from the biogeochemical processes. And what kind of processes? It could be, for example, point source release, it could be desorption of phosphorus from stream sediments, and so on. And because of that, we see that in space, chemostatic response is more seen in high order streams, whereas those kind of higher slopes, CQ slopes, are prevalent in low stream orders. And the same is valid in time. So high magnitude storm events with high hydrological forcing will have more chemostatic versus low magnitude storm event, more chemodynamic response. So here we assume that we have straight line. The relationship is a straight line, which indicates that the flow increase is in proportion to concentration change, and that the maximum flow corresponds to a minimum maximum concentrations. However, from high frequency data, we know that this is mostly not often the case. And we see instead those kind of loops that we call hysteresis loops. And they result from concentration maxima or minima occurring either before or after maximum flow. And depending on which one is it, we have either clockwise or anti-clockwise hysteresis loops. So going back to that hydrograph and the chemograph, you might wonder, okay, so how does the secure relationship look like in this case? It looks like this. So it's pretty much lots of data points. It's really difficult to distinguish any pattern. But when we try to focus on individual storm events, then we see that we can we have those hysteresis loops I've been talking about, and also there is some transition, seasonal transition between more steeper slopes in the summer and more chemostatic responses in winter. So this is for total phosphorus. But when we try to plot this kind of secure response for different water quality parameters, what we see is that there is a large diversity in secure responses. So we have here 9 graphs corresponding to different water quality parameters, from total phosphorus, total dissolved phosphorus, turbidity, nitrate, nitrogen, dissolved oxygen, conductivity, redox potential, pH, and temperature. And on the horizontal axis, we have flashing. So -1 indicates dilution, 0 is a chemostatic response, and +1 is a concentration effect. And then on the vertical axis, we have the direction of the hysteresis loop. So is it clockwise or is it anti-clockwise? Interestingly, this is for the subcatchment of the Eden. We see that there is transition on a seasonal basis between clockwise and anti-clockwise responses. So for example, for total phosphorus, winter storms have more clockwise response, so concentrations respond quicker to flow than during summer. However, when we look at those different dilution flushing patterns, we see that most of the parameters have very narrow range. For example, pH is pretty much a chemostatic response all the way. Similar dissolved oxygen and nitrate. And 3 parameters stand out, and this is phosphorus and turbidity, so different fractions of phosphorus and turbidity. So here we have mostly concentration effects, sometimes chemostatic linear response, and not so often dilution, and that is understandable. So you might wonder, okay, but what does it mean for water management? It means that when we have those steeper, more chemodynamic CQ slopes, basically we have a larger variation in concentrations with flow. And for phosphorus, for example, concentrations can change over several orders of magnitude. They can change from 0 to 1 milligram per liter or even higher. And that can happen very quickly. Other parameters that have more chemostatic response, they respond much slower, and here the variation is not as rapid, but also not as drastic. So in a way, that indicates that phosphorus, turbidity, those are water quality parameters we have to measure more frequently, possibly on hourly basis, to capture the range of variation, but also to be able to determine load in an accurate way. When it comes to parameters with more chemostatic response here, the sampling frequency doesn't have to be as often, and sometimes even weekly measurements can be enough. So that was one of the UK catchment. But what happens in another system? So here we have a smaller headwater catchment dominated by clay soils, and the same type of graph, but just for one parameter, for turbidity, which is proxy for sediments. And again, this large variation is a dominant thing. So we have events that have concentration, that they are chemostatic. There are also some events that show dilution, which is quite unusual for turbidity. But there is this almost even distribution between clockwise, anti-clockwise, and linear storm event loops. And if we look at specific storm events, those secure relationships can change dramatically. So we can have almost linear response, a bit wider loop that is clockwise. The third one is anti-clockwise, to more complex shapes, dilution or figure 8 shapes. And the last two figure 8 shape CQ loops indicate that we have multiple concentration peaks. So for example, we have pre-event flushing of sediments in a stream, followed up by some later arrival of sediments in a stream. So there is again a large variation. So in this catchment, we were interested in understanding how secure relationships change, not so much maybe in time, but more in space. So in this catchment, we have 6 sampling points, and they correspond to different types of land management. So points 42, 43, they are upstream in the catchment. Those are wells draining fields. and those fields have different treatments. And moving on, 0.50 to 0.60, those are the endpoints for a in-stream remediation measured called two-stage ditch, while 0.67 is the outlet of the entire catchment. And here we have points for turbidity and conductivity. You can see that there is a larger variation close to source of sediments, so close to the field. And that variation is being reduced moving downstream towards the outlet. So we were interested in seeing if we can use a hydrochemical model to predict some of those CQ responses. On the left-hand side, we have one storm event and those 6 sampling points. And for each one of them, we have a CQ relationship. So we have flow on the horizontal axis and concentrations, turbidity concentrations on the y-axis. And you can see they differ in shape quite drastically, from more linear responses close to source, close to fields, to a very wide and open loop at the outlet. However, when we used a hydrochemical model and we wanted to replicate those, we weren't able, just for 4 points here, but the model only was able to predict the slope more or less correctly. However, we could not see this variation in CQ shapes. So some slides now to finish, to show you how we can use the high frequency measurements for management. And this is the graph showing the effect of dredging sediments from the stream. And we have 2 sampling points for which we had continuous turbidity measurements before and after dredging event. So the downstream point is in red and upstream point is in black. You can see around 9th of October, there was dredging, and we can see increase in turbidity. What is very interesting is how this load, the dredged sediment load, is moved downstream in the stream. So you can see that during the storm event that occurred a few days after, we see different CQ response for those 2 points, upstream, downstream. For downstream point, there is this additional pre-event peak, which is this clockwise loop, indicating that that is the load of sediment that has been moved after dredging. So that's one example of how we can use high frequency measurements. Another one is, as I mentioned, we had 2 drainage wells, and they were draining fields with similar hydrology, with similar land use. The only difference was that the LF field was treated with lime. So lime was spread and incorporated into topsoil. And you can see difference in water quality straight away. When we used turbidity measurements, we could see there's also reduction in sediment transport from those structure limed fields and drains. And that reduction was quite significant. It was up to 80%. So another example how we can use high frequency measurements. But I think the most staggering way to appreciate high frequency measurements is to see how different sampling frequencies, what is the effect of those on load estimation. So here we have 5 parameters: total phosphorus, total reactive phosphorus, turbidity, nitrate, nitrogen, and specific conductivity. And we have decreasing sampling frequency from daily, weekly to fortnightly and monthly. And you can see that sampling frequency doesn't make a big difference for nitrate and specific conductivity. However, we can get up to 80% underestimation for monthly sampling compared to daily for phosphorus and turbidity. And to go back to CQ relationships, there is a linear response between CQ slope and a load error. So for more chemostatic slopes, near zero slopes, we don't see much error, and the error increases in proportion to the slope. So those chemodynamic CQ responses are those that bear the largest load errors. And one of the last slides, just to show you that what we deal with is very dynamic. So here we have high frequency time series, and they show quite varied response to changing flow conditions. But what I want you to focus on is this tiny, almost not seen storm event 22 that happened in late summer in 2018. And you can see that single storm event was responsible for extremely high concentrations of not only phosphorus, not only sediments, but also nitrate, nitrogen. So water quality is changing, and as the frequency of those extreme hydrological events is going to increase in the future, we are likely to see this decoupling between hydrology and loads. So this is something to bear in mind. So conclusions and implications. I think that CQ relationships are useful to describe water quality dynamics. And this is because they encapsulate information both on the catchment processes, so what comes in terms of hill slope hydrology, but also they describe the stream conditions around the sampling point as well. And in general, we see very large temporal variation in both solid and sediment dynamics for all flow conditions that are driven by hydrology and biogeochemistry that change on seasonal and daily timescales. But there is also large spatial variation, and this one is driven mostly by land use and different land management practices, but also stream properties. What we see, and this is the real value of high frequency data, that most of those CQ relationships are non-linear, and they have some components that are predictable. For example, this difference between clockwise and anti-clockwise CQs depending on the season, but there is also some randomness in this, and that seemingly random response can result from different sequences of storm events of different magnitude. When it comes to using high frequency data in hydrochemical models, here you have to be very careful. Basically, those models and the data are not compatible yet. So we can use high frequency data to ground truth the model outputs, but maybe we would struggle to replicate the diversity of, for example, CQ responses with hydrochemical models. From the management point of view, there is a clear link between the type of CQ relationship and implications for load estimation. And here those chemodynamic CQs, so remember either up or down, can contribute to large load errors. High frequency measurements are very useful to track the secondary pollution, not only for sediments, but also for nutrients. And we can see how that pollution load is moving downstream the catchment. And the last point is that those relationships, we can understand them from high frequency data. However, they are not written in stone. They are changing in response to changing underlying conditions. So with that, I would like to thank you, and I hope you have lots of questions.